In this video, we're going to look at what happens when we compose a couple of reflections. So remember, composition of functions happens whenever we take the output from the first function and use it as the input for the second function. So in the case of transformations, what this means is we start with an original preimage set, or preimage, let's just say a preimage point. We do a transformation on that to get an output, which is an image point. That's going to be our intermediate image. Then we're going to use the image of the first transformation as the preimage for the second transformation. The final output is going to be the final image of the original transformation, of the original point. And you do this for all the points. So for example, we're going to compose two reflections. We're going to do this about, there are three possibilities. If we reflect over a line, and then we reflect again over the same line, then of course we end up right back where we started. So the first thing is we start with the preimage up here, A, B, C, which was in blue. We first reflect it over the line M1 to get the pink image of the first reflection, but then it becomes the preimage for the second reflection. Reflect it, and we end up right back where we started. So a reflection is its own inverse operation, or inverse transformation, because it takes it right back, every point right back to where it started. Now what happens if we reflect about a line, and then we reflect again about a second line that doesn't it's not the same line, but intersects. It's going to intersect at this point X. Here's our second mirror line. Okay, so there we go. So look what happens. So again, let's just take it one at a time. So the blue one reflects over to get the pink one. Can you see that? Okay, A is going to reflect over to here to A prime. Okay, B to B prime, C to C prime. Then we're going to take those and reflect again over this new line, M2, which intersects at point X, and we get the red, which is our final image. So here's the question. If we hide the first one, and we just go from the blue to the red, could you get that in one single transformation? If so, what kind of transformation would it be? Would it be a reflection? Translation? Rotation? Well, let's see here. If we were to connect up preimage to image points on the final here, well, clearly these are not the same length, so it's not a... They would have to be the same length and parallel for it to be a translation. They'd have to be parallel to each other to be a reflection. Could it be a rotation, maybe? Well, let's see here. If it's a rotation, we should be able to take that point of intersection X. Well, I'm sorry. If that's X is the center of the rotation, could it be? Maybe it is. If it is the center of the rotation, we should be able to take circles centered at X, going through A should go through A double prime. In fact, notice, look what happens. If we do center a circle at X, that circle contains A prime, and A double prime. Interesting. And if we have a circle centered at X that goes through B, it also contains both B prime and B double prime. And similarly, the circle going through C contains C prime and C double prime. So all of those points stay the same distance away from this point of intersection X. Maybe that actually is a rotation then. Does that make sense? Okay, if so, what would the angle of rotation be? Well, to measure that, we'd have to pick a point. Let's see. Here I picked A and went to X and then to A double prime. What is that angle? Well, I measured that. A to X to A double prime. And here it is about 39.2 degrees. Let me just make it something easy Can I make it 40? I don't know if I can or not. Let's see. That's real close. Really close to 40. And if I went from B to X to B prime, B double prime, it's the same angle. That's interesting. What about C? If I measure from C to X to C double prime and measure that angle, that's also 40. Let's see, let's make these all same size. So those were all 40 degrees approximately. Okay, interesting. Well, what was the angle between here? So if I take a point on the initial ray to X to another point on the terminal ray, terminal side there, and measure that angle, so from DX to E I've already got measured, it's about 20 degrees. So in fact, if you double it, what do you get? You get the same angle. Interesting. Okay, so what's the conclusion? Conclusion is the composition of two reflections about intersecting lines is equivalent to a single rotation about the intersection of the two lines through an angle twice as big as the angle between the two lines. Interesting. Now, there's another possibility. We did the same line twice, which gave us the identity transformation. We got a reflection about the same line twice. A reflection composed with itself is the identity transformation. We now have the reflection about one line composed with a reflection about another line is a rotation. What about if the two lines don't intersect? That's the other possibility. So here we have parallel lines. Oops, don't jump to the conclusion here. Okay, so here's our first line, and there's our image. Where's our second line? Well, maybe it's over here, and now you can see the image there. Does that make sense to you, the way that looks? And of course, this is all, like everything else, this is dynamic. I can move around these things here. This line, I can move around this line here. Okay, but I've made these lines parallel. So if we can hide the intermediate one, how does the red one compare to the blue? Well, let's see here in just a minute. If I connect up pre-image to final image, like this, this, and this, what does it look like for those three? They look like they're the same length and parallel. Maybe this is a translation then, huh? Looks like a translation. Could we check that? What would the vector be? Well, this would be the vector. So if I mark that vector and then just simply take this figure here and translate it by that vector, there it is. Look at that. It went right on top of the other one. So in fact, at least at the moment, it actually is. And if this one stays blue, it'll be on top of the red. Sure enough, it is. Okay, let me get rid of that. Alright, there it is, back red again. Okay, well, how does that vector relate to the original two lines? Because originally we were just given the two lines, which were parallel. Well, if you look, it's right angles there. So we know the direction of it, it's perpendicular to the two vectors, and it kind of goes in the direction of first line to second line. So it's going in that direction. But if you look, it's further than that. So we may need to measure some distances here. So if I measure the distance, say, from there to there, from G to H, and then I measure from A to A prime, look at that, 6.23. And of course, if I measure from B to B prime, it's also 6.23. How do these relate? Well, if you take the 3.11 times 2, well, of course this has more digits, you do get, if you double that one, you get this one. So again, we get something doubling going on. So remember when we were intersecting line, the conclusion was reflection, then a reflection gave you a rotation, and it's equivalent to a single rotation about the intersection of the two lines, but the angle was twice as big as the angle between the two lines. If we compose a reflection and a reflection about parallel lines, the conclusion is it is actually a translation, but it's in the direction of the first line to the second line, perpendicular to both lines, and it's through a distance twice as much as the distance between the two lines. So, very interesting. So, if you compose two reflections, you either get the identity transformation if it's the same line twice, a translation if the two lines are parallel, or a rotation if the two lines are intersecting. And in fact, the converse turns out to be true as well. Every composition of a reflection about two parallel lines gives us a translation, but the converse is true, which says every translation can be made up of as a reflection about two parallel lines. So one example of the two parallel lines to get you to the image point would be just draw the vector between here, and if you would just if you would break it off, basically any two lines that are perpendicular there, where the distance here is half as much as the distance here. So, for example, you could break it into fourths if you wanted to, and then from the go a fourth of the way from A to A prime and a fourth away from A prime to A, and those you could put your two lines there, among other places. So, not necessarily a unique way of doing it, but it can always be done as a composition of two reflections. Similarly, turns out every rotation can be thought of as a composition of two reflections as well. You just take your center of your rotation, and we've just got to make two lines going through there, and we just need to make the angle between the two half as big as the angle between as the angle of the rotation, basically, and we should be able to work that out. And of course, the identity we can even think of as a composition of two reflections, a reflection about a line, and it's the same reflection again. So we see that all those types of things, those types of transformations, really boils down to just building them up out of reflections. So you want to think of your reflection as sort of the building blocks or the basic kind of transformation, and everything else can be built up out of that. Turns out that reflections, rotations, translations, and then there's a fourth type called glide reflections, and then the identity, I guess, is a fifth type. All of those turn out to be exactly the kinds of transformations that are called isometries. They map congruent figures to congruent figures. Now remember, we actually defined what we meant by congruent figures in terms of triangles, line segments, line segments first, and then angles, and then triangles, and then quadrilaterals. We define those without referring to transformations. And so we can see that they will map congruent figures to congruent figures based on our old definitions of congruence. But now this gives us a nice way to generalize our definition of congruence now to talk about congruent figures in general. And we can define two figures as being congruent if and only if there exists an isometry, that is, a reflection, rotation, the identity transformation, translation, or glide reflection. One of those isometries, if it exists between the two figures, then they're congruent. And this goes back to the intuitive idea of basically cutting one figure out and placing it on top of the other one, perhaps with a reflection, rotation, translation, etc. Okay, so that's kind of interesting, and that's going to lead us to this idea of composition of functions in general. is going to lead us to think of these things as operations on this set of isometries. So we'll come back and see what kind of structure that has a little bit later in one of our other videos.